For this lecture, we will be discussing the Laplace transforms. So this is the first out of 4 parts of the lecture. So for the Laplace transforms, this one is just basically a short reading, short excerpt of Neil Armstrong this press conference. However, what are these Laplace transforms used for? You'll notice that some differential equations can only be solved by Laplace transform. So they're easily solved using the Laplace transforms, right? So when you took the differential calculus, you learned how to differentiate, and then you learned how to integrate in the integral calculus, and then combined, we are learning how to solve differential equations. For example, you have this. G of alpha is equal to the integral from t1 to t2 of function of t, k of k, so this is another function of alpha and t dt. So typically, the Laplace transform is written in this form, the second one. So the Laplace of the function of t is the integral from 0 to infinity of e raised to negative st times the function of t dt. And eventually, the Laplace of any function of t is actually a function of s. So where do we use this? Typically, these are very useful, especially in control systems engineering. So for the ECEs out there, for the computer engineers out there, and mechatronics, mechanical, manufacturing engineers, this would be very useful for you. For chemical engineers also, for control systems, industrial engineers, civil engineers. So basically, for all engineers, this would be very important. However, please take note of this. Not all functions have Laplace transforms. There is an important class of differential equations where only Laplace transforms will work. So please take note of those. So let's try to derive, the simple Laplace transform. So if you are given a function of t is equal to k, so what is the k here? Your k here is actually a constant. So that is a constant. So the Laplace of a function of t is basically the Laplace of that k, Laplace of that constant. And then applying the concept or the formula that we have here, that's from e to the infinity, from 0 to infinity of e to the negative st times k dt, right? So since k here is constant, you can choose to move it out in front, right? And then in here, the only function declared is t. So I can say that if u is equal to negative s of s times t, my du would be negative s dt. So that means I need a negative s, I need a 1 over s that is negative in here. So this is basic integration. So with that, I have, you can also bring out the k. So you'll end up having negative k over s e to the negative st from 0 to infinity. However, you have to take note that this one in the integral, it's an improper integral because one of the limits is infinite. That's why you can see here the limit expression. So limit of e to the negative st as t approaches infinity, and then here it's e to the 0, you'll notice that the answer, the very, very long process that it has to undergo, but the answer for this one is simply k over s. But this is acceptable when s is greater than 0. However, I want to show you here in this one that there are tables. Look at this. Earlier, I showed you how to derive the formula. So if the function of t is k, the answer is k over s. However, there's actually a table of formulas for this. So if the function of t is simply a constant, the Laplace is k over s. Again, when you are asked to solve for the Laplace of any function of t, your answer would be a function of s. That's why you notice here the answer is k over s. For e to the at, it's 1 over s minus a. For t to the n, it's n factorial all over s raised to n plus 1. Do take note that n is an integer that's greater than 0. For cosine kt, where k is a constant, it's basically s all over s squared plus k squared. For sine of kt, it's k over s squared plus k squared. Now, this is the next page of the tables. So for hyperbolic sine kt, it's k over s squared minus k squared. So when you compare these two formulas, hyperbolic cosine gives you s over s squared minus k squared. So how is this different from the basic or the plain sine and cosine? These ones are positive. The other ones are negative. Okay? Let's go to the next slide. So some properties of the Laplace transforms. Again, the Laplace of a function of t. When you apply this formula, you'll basically just end up with a function of s. And when you have two functions being added, you can separate the Laplace, apply the Laplace to each of them. However, when you have a product of two functions, you can't just separate the Laplace. So what you do here is multiply first the function and then apply the Laplace afterwards. For example, I want you to please look at the table that you have. Let's try to apply. What is the Laplace of a constant there on your table? Diba, k over s. So I can see that this is 3 over s. Now, the 4, I don't need this. You can choose to bring it out. Now, what is the a, or what's the coefficient of the t in here? It's negative 7. So if it's in this form, I can say 1 over s minus negative 7. So this is s plus 7 at the bottom, and then there's minus 4 on top, in front. I can place that on top. In here, you'll notice there's no e, however, there's a t. So this is 6, you can bring it out, 3 factorial all over s raised to 3 plus 1. So it's this one. Let's try this. So for this one, guys, can you help me answer this? The problem with this, guys, is there is a product in here. So how do you solve something like this? There's a product. You can't have a product, as I said, so you multiply them. However, do take note of this. So if we can recall, sine 2 theta is basically 2 sine theta cosine theta. Sine squared theta is 1 minus cosine 2 theta all over 2. And then cosine squared theta is 1 plus cosine of 2 theta all over 2. So let's try to recall these. So I can safely say that this one, upon simplification, I can see that this is basically 2 times 2 sine 2t cosine 2t, right? This one, I don't have a square so far. So, but then cosine squared, I can say it's this one. So 1 plus cosine of 60 all over 2. So let's fix this first. Your f of t at the moment is 2 sine of 4t minus 1/2 minus 1/2 cosine 6t. Now, I would like to get the Laplace of these ones. So the Laplace of the function of t is 2. Can you help me with the formula? For sine 4t, what would be the answer, guys, using your table? S squared plus 16 minus, this is a constant. What would be the answer? Over S, tama? Minus, I don't need the 1/2. What's for cosine? S squared plus 36. Therefore, I can see that my f of s is simply 8 over s squared plus 16 minus 1 over 2s minus s over 2 quantity s squared plus 36. That is your Laplace. All right. Let's try the next one. I don't need the 3. I can bring it out. Can you give me the Laplace of sine 5t? 5 over s squared plus 25. Very good. This one, I don't need the 26. I can bring it out. What about for cosine 2t? Plus 4. Therefore, this is simply 15 over s squared plus 25 minus 26s all over s squared plus 4. That's correct. This is your f of s. Okay, next, let's practice. So for the next page, you have hyperbolic cosine. So looking at the table, how would this be? What is your f of s? I gave you a formula for this. Over s squared minus 9, right? So that's the final answer. Now, looking at the right, I don't have something like this. Maybe it would be best if we separate this. So I can say this is 1/2 e to the 3t plus 1/2 e to the negative 3t. So this is your function of t. So what I would want to do is get the Laplace of that function. So for the plus, sometimes it's a cursive letter L or sometimes it's just capital L. Okay, can you please give me the Laplace of this one? One over s minus 3, that's correct. Plus 1/2 of what? 1 over s plus 3. So that means if I remove the 1/2, I'll end up with s minus 3 and s plus 3. So this is s plus 3 plus s minus 3. 1/2 times 2s over s squared minus 9. And simplifying this, you'll end up with s over s squared minus 9. So some of you might ask, how is that possible? Like, it's a different problem, but they had the same answer. Because if we can recall that for hyperbolic cosine, let's just say of ax, that is e to the ax plus e to the negative ax all over 2. If you can recall this from your differential calculus, that's the definition of hyperbolic cosine. So basically, the two problems are the same. So they end up having the same final answer. All right, so I gave here a lot of problems. Let's try solving. 2 factorial all over S cubed, tama? Plus, I don't need the 4. 4 na lang siya. And then, what's the Laplace? 1 over s squared. What about for the constant? What will that be? 5 over s. Very good. So this one is basically 2 over s cubed plus 4 over s squared minus 5 over s. So that's correct. This is your Laplace. Or sometimes, if you want to combine them, you can say over s cubed, that becomes 2 plus 4s minus 5s squared, if you want to combine them. Okay? Now, let's go to this. What is the Laplace of e to the negative 2t? Look at your tables, please. S plus 2. Exactly. So that's the final answer. 1 over s plus 2 plus 4 over s plus 3. That's correct. This is your Laplace. Sige. Sige nga, let's try this one. It's minus 25. Plus, therefore, the answer is 15 over s squared minus 25 plus s over s squared minus 9. That's correct. That is the function of s. Next, please. Negative 1/2 all over s. That's correct. All right. So when we rewrite this, I can say that's negative 1 over 2s plus 2 over s plus 1 minus 1 over s minus 4. That's correct. This is your function of s. What about this one? This one, take note, it is squared. I didn't give you anything that was squared before. So what could you do? We distribute or basically just expand. So when you expand this gives us cosine squared of 2t minus 4 cosine 2t sine 2t plus 4 sine squared of 2t. Therefore, now I have removed the square. And then, again, let's recall the formulas, the double angle, half angle. So, I'll just write it here. Sine 2 theta is 2 sine theta cosine theta sine squared theta 1 minus cosine 2 theta all over 2 cosine squared theta is 1 plus cosine 2 theta all over 2. All right. So using those concepts, what will the first be, guys? Let's apply first the concept of cosine squared. That becomes 1 plus cosine 4t all over 2 minus this one. This is basically 2 sine of 4t. And then this is 4 times 1/2 of 1 minus cosine of 4t. I just tried to rewrite them. So this one would end up to be 1/2 cosine of 4t minus 2 sine of 4t plus 4 over 2 is 2 minus 2 cosine 4t. And you'll notice here, guys, that this is a cosine 40. That's a cosine 40. This is a constant. That is a constant. So maybe you can combine them first before doing anything. So let's start with a constant. 2 and 1/2, that's 5 over 2. Negative 2, positive 1/2, that's negative 3/2 cosine of 40 minus 2 sine of 40. So now we're finished. Can you give me the Laplace, guys? 5 over 2 all over s. That's correct. Next. S squared plus 16. Very good. S squared plus 16. So this one becomes 5 over 2s minus, maybe we can just write this outside. It's okay because it's a fraction anyway. And then this one is minus 2 times 4 is 8 over s squared plus 16. So that's correct. This is your function of s. So here, let's try this, guys. Let's try mentally. Go. 2 times 3 all over s to the 4. That's correct. Minus so 3 factorial is actually 6 times 2. That's 12 over s4 minus 3 over s plus 1 plus 10 over s squared minus 25. That's correct. So this is your Laplace.